Well, next talk is from Matthew Pressland from University of Leeds, and he will talk about a cluster character for I variables.
Muchas gracias. Thanks for the invitation and to speak here. It's very nice to be really anywhere at all, but it's particularly nice. So this is some joint work with Grabowski, and it's not yet available. I mean, it's part of a larger project which is still in progress. I just want to explain a small part of it. So I'm going to start by recalling, which we've already seen today, a seed, which for me will consist of a quiver Q, so I'm just doing skew symmetric things, a set X of X variables, but then also a set Y of Y variables using Fomin&Zelevinsky notation. And if I choose additionally a vertex of the quiver Q, which would be mutable, so implicitly the quiver now has frozen vertices which I should not choose, then I can define mu K of S, the mutated seed, by taking the Fomin&Zelevinsky mutation of the quiver, which for this audience I won't define, the mutation of the X variables, which is as we saw in the previous talk, I change exactly one variable for another, and the mutation of the Y variables, and since I think this actually does appear less frequently in representation theory, and I would admit that I had to look up the exact formula before giving the talk, I will write this down. So what happens is that the ith cluster variable, the ith Y variable, is multiplied by some number of copies of YK, as many as the number of arrows from I to K, and then also by 1 plus YK to the number of arrows K to I, minus the number of arrows from I to K. This is if I is not equal to K. So in this version of mutation, almost everything is changed. And the Kth variable changes only very slightly. It's replaced by its inverse. So I did need to say, I know that sometimes for people online, it can be difficult to read the board. If the camera is focusing, the notes for the talk should be in the chat if we want to check something in there. Okay, so my goal is to try and categorify this picture a bit, and categorify the Y variables in the picture. But to do that, I'll want to start by reminding you a bit about categorification in general. So I'm going to start by discussing the index and co-index maps. As a reminder, which we've already seen. So first, the general setup, I'll work over an algebraically closed field. And E will be a K-linear Frobenius exact category, which should have cluster tilting objects hereafter just CTOs, such that several things are true. Firstly, E should be Hom finite. Secondly, if I take the stable category, I mod out by the projectives, this is famously a triangulated category. It should be 2 Calabi Yao. So this is the kind of category that is perhaps more familiar to some people from cluster categorification. For every cluster tilting object T in E, the quiver of its endomorphism algebra, and I always take op for conventional reasons, has no loops for 2 cycles. It's a finite dimensional algebra by assumption 1, so it has a Gabriel quiver, and I will now put those quiver. And one that might look a little bit strange to some people. Again, for all of these cluster tilting objects, the global dimension of this endomorphism algebra should be bounded by 3. Okay. So this last assumption might look very strong, particularly if you're used to thinking about triangulated cluster categories where it absolutely will not hold. But since I'm doing the Frobenius case here, this is actually equivalent to the statement that E is the category of Gorenstein projective modules for B Iwanaga-Gorenstein, as Nora defined last week, with Gorenstein dimension -3. And almost every example of a Frobenius categorification of a cluster algebra in the literature that I know is known to be equivalent to a category of this form. There are a few where I don't know it, but I don't know it's false either. This is the generic situation. So some comments. I mean, I think what I'm going to go on to say can be done in the triangulated case, but I find it slightly easier to present this version. What else? Hom finite is not strictly necessary, but you do need some kind of finiteness assumption. Again, I'll just keep things simple. And this assumption 4, together with 1, mean that in fact the condition that these quivers have no loops is automatic by the no loops theorem. So the only real condition here is the 2 cycles. Okay. Now let me give a proposition and definition at the same time. I forgot to check who to attribute the proposition part to, so apologies for this. If I take an object U in E and a cluster tilting object as well, then I can find short exact sequences. Let me make sure my notation matches my notes. That look like this. The first one ends in U, the second one starts in U. This notation is perhaps a bit clunky, but I don't use it very much. The things which are called T with some decoration live in add T. And then not go off the bottom of the camera. The index of U in T is the difference T plus minus T minus of the terms appearing in this left-hand sequence. Co-index, I promise this is the last thing I'll write on the board, is the difference of the terms in the right-hand sequence. And both of these, for me, Piegi might object slightly, but for me, they live in the Grothendieck group of add T, which is just an additive category, or if you prefer, an exact category with the split exact structure, because T is rooted. No, I'm not supposed to use that now. This isn't very fast. Okay. Okay. Yeah, the proposition might be due to Day and Keller, or it might predate this. I think there's probably different results in different categorical contexts. The theorem, which I am sure is due to Day and Keller from 2008, is that if I take 2 cluster tilting objects, then I can take the index into T of objects in T prime. So I'm thinking of this now as a map from the Grothendieck group of that cluster tilting object. It goes into K0 of add T. And the theorem is it's an isomorphism, and the inverse is the co-index in the other direction. These are inverse isomorphisms. Okay, so now for the rest of the talk, I'm just going to fix a cluster tilting object T. This is going to behave like my initial seed. A will be its endomorphism algebra. A underline will be its stable endomorphism algebra. and Q will be the quiver of A, treated as an ice quiver where the frozen vertices correspond to the projected injective summands of T. And later, when I have a cluster tilting object T prime, A underline prime, Q prime will be defined in the obvious way. Okay. So one final note before we really get going. I will use in the background all the time the nadir isomorphism from add T to proj A, which is given by applying pom T blank. And I'll use it to identify the growth in the group K0 add T with K0 proj A. So in particular, I can view the index and co-index as taking values in this lattice, and I won't make a big fuss about that. I'll try not to make a big fuss of it. Okay. Now let me define another map of lattices. This will be called beta. And this goes from the growth in the group of finite dimensional modules for A underline, so for the stable endomorphism algebra, to K0 proj of A. And the map, I'll say in words, is I take minus, for some reason, the class of a projective resolution. So an A underline module is in particular an A module, just one with a restricted support, and A has finite global dimension. So this makes sense to do. Okay, should probably move to another board. So it's this description of beta, that's why I wanted to explain things in the Frobenius case, but you can, and I will shortly give an alternative description of beta. So that, which also makes sense in the triangulated case, but it's a bit more unnatural seeming. Okay, getting a lot of exercise. Okay. So now a proposition just to collect some facts about beta. So the first thing is that for any module in this category of finite dimensional A underline modules, there's some U in E, not unique, but its non-uniqueness can be quantified, such that M is isomorphic to G of U, and here G is functor X1 on T. Right? So this functor vanishes on projective injective objects, and so it always takes values in this subcategory of mod A. This is, again, the attribution's a bit complicated. I think in different contexts, this is Fu&ndash, Reiten, Keller, Reiten, and a quite general formulation which I like is in Koenig and Ju, and I'm sure there are more. Good. And then the property of this U, I mean, what's good about this U, beta applied to the class of M is actually the co-index of U minus the index of U. Right? So this is the formulation, which makes sense in other categories as well. But here, this is computing a projective resolution in a way. The second thing is that my growth in groups have preferred free generating sets. I'm just going to say basis because it's quicker. So the first one is given by the classes of simple modules at the mutable vertices, and the second by the classes of indecomposable projectives. And just one little reminder about the UNADA for some notation. I mean, each one of these is just Hom over E from T to Ti, where Ti is an indecomposable summand of T. So I can use either the indecomposable summands of T or the indecomposable projectives, same difference. And if I use these bases to write the matrix of beta, what I get is the exchange matrix of Q. Okay, so that was the reason for the choice of sign. This again is quite well known. You can find it in Fu and Keller, but maybe not formulated exactly like this. Not so far away from it. Okay. So now, before I give the main result, I mean, we should have something to compare it to. I'll give you a reminder about categorification of X variables. So the definition of the following function is due to Fu and Keller from 2010. And I take U in E. I still have my fixed cluster tilting object T. I'm going to define X of U to be X to the index of U times the sum over submodules of G of U, X to the beta of their class. Okay, so this is an element of the ring of functions on K0 proj A. And yes, let's just leave it at that. Okay. While I'm erasing, you can contemplate the legality of what I've just said. Explain it. Okay, so maybe I can start the same words before I write it down. Of course, the summation here could be infinite. This module could have infinitely many submodules, but it is finite dimensional, so they only have finitely many dimension vectors. And I'm just going to count families by the Euler characteristic of the appropriate quiver Grassmannian. So maybe that's sufficient then to just write count these submodules by Euler characteristics. I'm not intending to claim that these characteristics are not important. They certainly are, but I don't want to keep writing them. I'm going to do this trick several times. So. And the other thing is that if you want to put this object in a more familiar place, you just use my preferred basis again. So this ring is just a Laurent polynomial ring in n variables by setting xi to be x to the class of vi. Okay. So then the theorem same paper, also from 2010, is that under all my standing assumptions, this function is a map, or can be seen as a map, from indecomposable, reachable, rigid objects in E, i.e. the indecomposable summands of things, of cluster tilting objects which are obtained from my fixed T by mutation. It maps to the X cluster variables of Q of the cluster algebra determined by the ice-quiver Q, and the theorem is that this is a bijection. Okay, and if, for example, it induces a bijection from reachable cluster tilting objects to clusters. Right? Okay. Right. Okay, so that was X variables. Now what do we do for Y variables? And really, just the naive observation is that, well, everything should be dual. So let me introduce some notation for duality, which is a check mark, which will mean duality for abelian groups, so Fomin to Z. And a somewhat standard representation theoretic fact then for these kinds of algebras is that the dual of K0 proj A can be naturally identified with K0 FDA, because the dimension of Hom pairs the projectives and the simples as two dual bases. What's going to happen? We'll raise the bottom half of the board in a minute. I need a break. Okay, so definition. I mean, if I recall, I have my co-index isomorphism decorated with a T prime now, from K0 proj A to K0 proj A prime. So if I dualize this, I get a map which I'll call ind bar sub T from K0 FD A prime to K0 FD of A. And I can define co-ind T bar similarly. Oh yeah, and that's the other thing I should say. So you can check, it's not, I mean, it has to be checked, but it's not so hard. That if I look at the sublattices for the stable endomorphism algebras, then this restricts to an isomorphism of those. So the restriction behaves nicely. That's effectively just that the index and co-index don't do anything to projective injective objects. Okay. I should skip this. Okay. Oh, I need to make more space. Okay, so let's try and understand these maps a little bit. So the first proposition, this is now us, is that if I take a module in here, okay, this is x1 t prime of u for some u, then yeah, I can write beta of m. Remember that was co-ind m minus ind m, almost uniquely as a difference of two summands of t prime, summands of t prime. Sorry, so this should be beta prime. Okay, these are unique up to common summands, and in a minute any common summands will cancel each other out in the construction that comes later. So you can actually make any choice you like, but there is a kind of canonical minimal one. And then the claim is if I do the dual thing to m, I take its co-ind bar minus its int bar into t. Well, that's just the class of this tm plus minus the class of this tm minus g. So g is x1 into t, so I get finite dimensional A underlying modules. So I land in here. Okay, this probably looks a bit mysterious. If you treat the case when M is a simple module, then these objects are recognizable. They're the middle terms of some exchange sequences. But they exist in general. Okay. So now I should write down the formula. Is the following. So I'm going to take M as here. Y of M is y to the ind bar of M times the sum over submodules of G of Tm plus y to the class of the module times the sum over submodules of GTM minus y to the class of the module inverse. And again, I'm pulling the same trick with the Euler characteristic. So if these families are infinite, then I have to put Euler characteristic coefficients in there. Okay. This is in the ring of rational functions now on this Grothendieck group. And again, I can identify this with the ring of rational functions in as many variables as there are mutable vertices by using my preferred basis. So yi is just y to the simple module. Okay, just have time to state the theorem. I'll just give a couple of remarks. Okay, so while I'm erasing, so Pieggi told us on Monday that G vectors, the index is to do with G vectors. It categorifies G vectors. If you look at the definition of ind bar, I constructed it by taking the inverse transpose of the index. And so if you know tropical duality, you should not be surprised that this function categorifies C vectors, or the C matrix, really. Okay. Good. So here's the theorem. I take this map Y, I view it now as a function from the set of simple modules for the endomorphism algebra of T prime as T prime, no, I shouldn't write there, I will read it, for all T prime mutation equivalent to T. So typically this is an infinite set of algebras and I'm taking all of the simple modules. It maps to Y cluster variables or Q underlined, so the mutable part of the quiver, the principal part of the quiver. And the theorem is it's surjective. Okay. Okay, very quickly, I'll just give one or two remarks. Then, so the first remark is that it's not injective. So this is not just something we can't prove, it's just not true. This is if you thought about Y mutation, when you mutate a Y seed, any variables which are very far away in the quiver are not connected by arrows, don't change. But of course, here I change the entire algebra, so I get a completely new set of simple modules. So thinking about when two simple modules for different algebras actually map to the same place is probably an interesting question that we need to follow up on. But this is a disjoint union over cluster tilting objects, so it definitely can't be injective. I promised a cluster character. So I should point out that it is a character. This is not very hard to see. So if I have a short exact sequence of modules, then the character of the thing in the middle is just the product of the things on the outside. Sorry about that terrible board usage. Okay, so this would say M is M1 plus M2 in the Grothendieck group. Y takes that sum to a product. And the final remark is that the proof that we have at the moment is somewhat unsatisfactory, at least from my point of view. Or perhaps it fits into the point of view, into the title of the conference, and that it's an application of cluster algebras to representation theory rather than the other way around. So the proof is by comparing this formula to the separation formula from Fomin-Zelevinsky, cluster algebras 4. So the ingredients in this formula, C vectors and F polynomials and so on, it's understood how they categorify. So we can check with a little bit of work that this formula is actually equivalent to that one, and the separation formula is true. Now, in principle, and this is sort of something still to do, it should be possible to prove our formula by a kind of inductive argument, doing purely categorically, doing mutation in the category, and then we could reverse the logic and get a categorical proof of the separation formula. But at the moment, the logic is the other direction. Okay, I think that's all I have time for.
Okay, thank you, Matthew. Are there any questions? A question in the room? No questions? Okay, if there are not any questions, we thank Matthew again. And we come back in 14 minutes.
We should just move them. Easy to have a question. Is that enough for you?
Matthew?
There were some questions here. Are you there?
I'm still here.
Okay, there was a question here. The X and Y character approach. Matthew?
Yeah, I can hear you.
You can hear me?
Yes.
Yes. There's a question that says that if the X and Y character approach.
What is the relation between the X and Y character approach?
Should be possible to be more precise, but I mean, I would say duality. That so would have been nice to have time to point out. I'll move the formula now. The denominator in the X cluster character formula, for example, is just this G of U. If you and I sum over submodules of this. So if I take the whole module and I compute the exponent, what I get is co-index of U minus index of U. In the Y formula, I have these two summations, say over G of T of M plus and G of T of M minus. One of the sums is inverted. So I claim that's sort of natural to think of that as a kind of Y polynomial for the difference, F polynomial for the difference, G Tm plus minus G Tm minus. Again, if you take the N to be maximal in both cases, the tropicalization will give you a term sort of at the other end of the function where the coefficient is co-int bar minus int bar. So it has, they have the same flavor of kind of interpolating over some poset between the index and the co-index. And really the ingredients are kind of dualized step by step. So you kind of follow your nose with the duality and then prove that you got it right in the end. Does that answer the question?
Well, there was another question. In the surface cluster algebra case, does your formula as a radio compare with the formula for the X variable as cross radio?
Possibly. Sorry, let me just look at something in my notes which I did not say. I'd have to think about that. One thing you can read off quite straightforwardly actually is a formula for a Y variable as a quotient of X variables, I mean, up to some change of coordinates, which is effectively the definition of what Fomin and Zelevinsky call Y hat, but now sort of seed independent. I think you're asking me something the other way around, so I'd have to go and look at this surface formula, but I don't know. I guess the one other thing to say is that if this is very special to the surface case, it might be hard to see in the categorical setup because I haven't made any assumptions that would put me in that specific setting. So if it's something that doesn't hold very generally, then wouldn't perhaps know what the extra assumptions to make to be able to see it again. Let's see, Volker has another question.
Okay, there is another question. Can one translate the two into each other by staying in the world's cluster algebra without going back to the category?
You should ask Fomin and Zelevinsky, but yeah, I think so. I think this is what the mirror symmetry people call P-star. I mean, this map between the cluster varieties. That's what beta is doing for us. But again, the translation is a bit, I would like to be able to say more precise things about this. The translation is a bit indirect because they're just different numbers of variables. So it's not that they're not in bijection with each other or anything like this. So trying to make a precise sentence about how the two formulae are related, I don't quite feel confident doing that. They clearly have a lot in common, but I think if you just want to stay in the cluster algebra setting, then look at cluster algebras 4 and how Fomin and Zelevinsky get the separation formulae, or a recent survey by Nakanishi where he does similar things in a slightly updated language. I don't think I can answer this myself right now.
Okay, thank you.
Thank you.